Hello everyone, and welcome to CRAMSURG, Clinical Research Appraisal and Methodology for Surgical Trainees, where we pick a paper fresh from the press on a hot general surgical topic. We review it for you, we present it for you, we critique its methodology for you, and provide top-of-the-field expert opinion and teaching on research appraisal and methodology. My name is Gio Perrin, and together with Professor Sababala Subramanian and Maria Digby, we bring you CRAMSURG from the wonderful region of the Yorkshire and the Humber. Welcome back, everyone. Today we're going to have a chat about a paper with a slightly different cut compared to usual. We're talking about a new technology that uses seismocardiography as a mean of estimating cardiorespiratory fitness. And particularly, we're going to talk about an initial study on healthy volunteers that was recently published in the Cardiovascular Digital Health Journal. Following that, we're going to have a chat about how this particular type of technology fits with the ideal framework. And we're going to have a general chat about the paper itself. I'll leave you to it.
The paper we're going to discuss today is validity and reliability of seismocardiography for the estimation of cardiorespiratory fitness. And I think this session's running a bit slightly different to how it normally does, because we're going to focus on discussing the ideal framework and how this technology could potentially fit into the ideal framework. So this paper was published in the Cardiovascular Digital Health Journal in October 2023. The aim of today's session is to review the paper, and we're going to discuss the SESMO-FIT technology. We're going to explore the ideal framework in a bit more detail, and then we're going to discuss how SESMO-FIT fits in with the ideal framework. So just to give you a little bit of a background into fitness in surgery. So cardiorespiratory fitness is a strong predictor of all cause, all disease mortality. And we all know that fitter patients do better. And because of this, the American Heart Association have recommended fitness testing as a vital sign. But the current methods of fitness testing, or our gold standard fitness testing, is CPET, which essentially involves a lot of equipment, expensive equipment. It's quite a big thing to do for patients, and you need professionals to interpret the results and run the test itself. So it's quite expensive, and currently we perform about 30,000 CPET tests preoperatively in the NHS each year. So there's been a drive to develop non-exercise methods of fitness testing as a proposed pragmatic alternative to CPET. But currently we don't have a reliable method for clinical practice. And this is a photo of what CPET involves for those who may not be aware. So this is Ventroject. It's essentially a very small device that sits in the middle lower part of a patient's or a participant's sternum. They lie flat and still for about 120 seconds. What the device does is it picks up vibrations of the chest, which are made by the beating heart. And this generates a waveform, a bit like a SATS probe or an ECG. And different parts of this waveform correspond to different parts of the cardiac cycle. And the team who developed this technology found that aortic valve closure highly corresponds with a VO2 max when compared to CPET. And from then onwards, they then developed this device and have had the ability to connect it to an application via Bluetooth. And essentially you connect the app to the device you're using. You input the patient's age, height, weight, and gender, and you essentially press start. It takes the reading, and the raw data from this waveform is then sent to a cloud-based machine learning algorithm, and within 120 seconds you have a VO2 max result on your device.
Regarding this paper we're going to discuss tonight, this study design, we're going to discuss it as per the PICO format to make it easy to everyone to explain. So the general hypothesis was the purpose was to investigate the validity and reliability of seismofit VO2 peak estimation in a healthy population. So what did they do in the study itself? So the population they picked was 20 healthy adults between 18 and 75 years of age. The intervention, obviously, that they did was this Ventric with this little device, and they compared it with what's commonly known as CPET or CPEX, and also another similar device called the Polar Fitness Test. And the main outcome they measured was VO2 peak or VO2 max.
In terms of the methods they used, there is experimental study design where they recruited the 20 healthy volunteers with an even split between sexes. And they also included people of multiple fitness levels, which were determined by the amount of exercise they perform in a week. They did the testing on 3 separate test days, and they gave a 48-hour break between test days, and they were conducted over a 14-day period. On each test day, participant underwent 4 readings. So they did 2 seismofit readings, 1 polar and 1 CPET. And then they performed analysis. So they split the analysis into accuracy and then reliability. So in accuracy, they were comparing the seismofit and the polar to your gold standard CPET. And they did a Bland-Altman plot analysis with 95% limits of agreement. They also completed standard error of estimation and mean absolute percentage error, and they determined that less than 10% is clinically relevant. They also completed Pearson correlation. In terms of reliability, they used within subject standard deviation and coefficient of variation. And then looking at the results, so I'm going to focus on seismofit versus CPET. So overall, on average, seismofit seemed to underestimate VO2 peak about 7% lower when compared to CPET. And the Pearson correlation was deemed to be high at 0.7. And when looking at the Bland-Altman, the mean difference was minus 3.1, with limits of agreement from minus 13.9 to 7.7. And when you look at the Bland-Altman for your polar fitness test, which is the diagram on the bottom right in green, you can also see that this polar fitness test seemed to overestimate VO2 peak when compared to CPET with a bias of 4.4, and the limits of agreement were slightly wider than your seismofit, suggesting that seismofit performed slightly better comparing to the gold standard than the polar fitness test. Their mean absolute percentage error was 12%, so slightly higher than their clinical relevant cutoff point of 10. When looking at the reliability, so they compared the 2 readings of seismofit that they performed on each test day, and they essentially found that there was no difference between these 2 readings. The correlation was very close to 1, and Bland-Altman demonstrated that they were essentially identical.
So in conclusion, the seismofit has shown high reliability and high to moderate accuracy compared to CPET, a better agreement to CPET than the polar, and the seismofit, the semi-sofit object when compared to the polar fitness test. So we said that we're going to talk about the ideal framework, and before we say that how this study relates to this, for those that don't know about it, so the ideal framework is a framework that was developed in order to improve research in surgical devices and non-pharmaceutical interventions. It's got 1, 2, 3, 4, 5 stages, starting from 0 to 4, and each stage describes the progression of surgical therapy research. If you see, on stage 0 is the preclinical phase, where usually the third-party person, like the company that has created the device, is sitting down with clinicians trying to figure out research questions and figure out how this device could fit into clinical practice. And then we go to stage 1, where we've got the first in-human study, where only a few humans, usually healthy ones or very, very unhealthy ones, are tested into the device, and we get some preliminary data in order for the device to progress to the next stage, which is stage 2, where we've got prospective developmental exploratory studies, like a mini cohort of patients or a bigger cohort of patients. And that study is it determines really the further stages of the study, and we go to stage 3, where we've got samples to compare, like case control studies, randomized control trials, etc., or massive multi-center cohorts. And the stage 4 is where we've got the long-term monitoring and the big registries of such devices. For example, devices used to detect hot lymph nodes during a cancer operation, etc., that stay in specific registries in the UK, America, and Europe.
Yes, so when looking at SESMOFIT, it's still in its developmental phase. And when I look at the definition of stage 2A and stage 2B, it seems to fit quite well in the stage 2A developmental phase. So Ventroject and SESMOFIT kind of doesn't directly fit with the ideal framework in the sense that it isn't designed especially for surgical patients. It's designed as a monitoring device essentially for anyone. They have just published a protocol in conjunction with Sheffield, where they're going to look at using the device in individuals with coronary heart disease. So essentially, they're looking at trying to refine and stabilize their work through small case series and improve it until it becomes a stable form. So the previous publications, when they've looked at VO2 max instead of VO2 peak, they've reached a state where they've adjusted their algorithms so that they can get accuracies of up to 0.9 with a mean absolute percentage error of 7. So that's kind of where they're at this stage.
So in summary, SESMOFIT is a non-exercise method for measuring fitness, maybe fitting for surgery as well. It's cheaper and significantly quicker than a CPET. It's got acceptable reliability, and it's showing improvements in accuracy, and it falls under the umbrella of stage 2A on the ideal framework. Thank you everyone very much for listening to this paper. Would now take comments and questions. Thank you.
I hope you enjoyed the presentation. We had quite a long chat after the presentation itself about a number of topics. We started by discussing the nature of the technology that we're dealing with and the theoretical basis for it and how it compares to the gold standard for the assessment of cardiopulmonary fitness, which is CPEX. And we discussed that on a theoretical basis, it might be difficult to accept how seismocardiography can be comparable with a much more invasive and detailed test such as CPEX, which involves continuous monitoring of ECG traces as well as oxygen consumption, CO2 production, as well as a variety of other cardiopulmonary variables. And with this on one end, it is hard to think that a measure as simple as seismocardiography could compare to such a complex data collection set, such as CPEX. On the other hand, we don't have to forget that ultimately what we're trying to estimate is the overall cardiorespiratory fitness of our patient. In this particular case, it's healthy volunteers, but generally speaking, would be our patients, and how that correlates with mortality. And ultimately, both CPEX and seismocardiography would be means to assessing that and measuring that. We then moved on to discuss a variety of other points, including how this fits with the ideal framework, and I think Avery gave a good overview of this during his own presentation together with Melissa. We then discussed data interpretation and algorithmic extrapolation of an estimate of VO2 max starting from seismocardiography data, and we discussed how ultimately algorithmic extrapolations, particularly in the context of proprietary apps, are often closed source, and milestones in development and changes to the algorithm can produce both wanted and unwanted effect. For example, perfecting the algorithm on a healthy subset of the population might not necessarily mean that the algorithm is as reliable in a population that lives on the extreme of the spectrum, like most of real-life patients actually do. And certainly changes to the algorithm itself can affect different types of populations differently in terms of their ability to accurately estimate VO2 max. And we moved on to briefly discuss how data transparency becomes essential in this context, and understanding how the changes in the algorithm affect the efficacy of the app become of paramount importance. And I think I will stop there before I get carried down the rant on open source versus closed source and open data. But if you're curious about it, there's plenty on the internet. I will leave you to it for now, and I'll see you next time. Thank you everyone for tuning in and listening. Until next time, keep running your life with our surgical podcast.